Successfully coating a product requires a delicate balance between the formulation of the coating and the process through which it is applied. In fact, even the most carefully crafted coating formulation can be rendered totally ineffective by uncontrolled variables in the application process. One of the most critical and surprisingly least understood of these is temperature. In this presentation, we examine the effect of temperature variations at the point of application on the performance of various coating formulations. Contrasting solvent-borne, waterborne, and 100% solids varieties, we begin with the intractable relationship between viscosity and temperature and explore how variations in this seemingly simple relationship can have a far-reaching and sometimes insurmountable impact on the performance of the coating system. We then apply these concepts, exploring the similarities and differences between two of the most common applications, spraying and rolling, and how variations in temperature can result in unforeseen consequences that can derail an otherwise sound coating plan. This logically culminates in a discussion of methods for controlling the temperature variable in modern coating applications. Let's start with the impact of formulation. It all began with solvent-borne coatings. Well, maybe not for cave paintings, but certainly from an industrial coating perspective. So this is where our story begins. All liquids show some change in viscosity as a function of temperature. Modern coatings are no different. Here we see the viscosity temperature curve for a common solvent-borne paint. It's the typical curve we're all familiar with. The nonlinear relationship, the viscosity falling as the temperature increases. Valspar recommends that this coating be applied at a viscosity of 26 seconds. If we extend this over to the curve and down, we can see that this correlates to a temperature of 28 degrees C. As long as it is held at exactly 28 degrees C, it will be at the optimal coating viscosity. But how often does that happen? Oh, right, almost never. And Valspar knows this, so they give us a tolerance of plus or minus 2 seconds to work with. Again, extending this over to the curve and down, we can see that this corresponds to a 3 degrees C temperature range from 26.5 to 29.5 C. So long as we stay within this relatively narrow temperature window, which is about 80 to 85 degrees Fahrenheit, we should be okay. In a system without temperature control, little can be done when the paint is above 29.5 degrees, and the resulting viscosity is below the lower 24-second limit. Other parameters, pressure, speed, flow, etc., must be adjusted to compensate. More often, however, the coating temperature is below 26.5 degrees centigrade, and the resulting viscosity is above the 28-second upper limit. The most common practice in this instance is to add solvent to reduce its viscosity. This plot shows the relationship between solvent addition and the change in viscosity. Now, for you chemists out there, we do realize that the total solvent versus viscosity relationship is exponential, but for this short portion of the curve, it is essentially linear. We can see that a reduction of 10 seconds will require the addition of just over 3% solvent by volume. This is the equivalent of adding about 6 liters to a 200-liter drum, 1.5 gallons to a 50-gallon drum, whichever way you want to look at it. Likewise, a reduction of 15 seconds will require the addition of nearly 5%, or 10 liters to a 200-liter drum, or 2.5 gallons to a 50-gallon drum. It's important to note that not only does this alter the carefully developed formulation, every bit of this added solvent will be driven off in the oven as the paint is cured, and in addition to the environmental concerns, represents excess cost in the process. To make matters worse, too much solvent can cause issues such as blister, pop, orange peel, low gloss, and even off-color defects. These factors combine to make minimizing solvent addition a worthwhile objective. To correlate temperature to solvent addition, we return to the viscosity versus temperature graph. Here we can see that the roughly 4.5 degrees increase in temperature from 15.5 degrees C to 20 degrees C produces a 15-second reduction in viscosity. Likewise, the next 5 degrees C from 20 to 25 represents an additional 10 seconds reduction in viscosity. So, this sequence shows that the 10 degrees C change in temperature from 15 to 25 degrees C has roughly the same effect as adding 16 liters of solvent to a 200-liter drum, or 4 gallons of solvent to a 50-gallon drum, again, whichever way you want to look at it. But an important and often misunderstood fact is that every paint formulation has its own temperature-viscosity relationship. Here we see the plots for 7 colors, all of the same resin base type, and formulated for the same application. These would all be considered the same paint, just of different color. Yet, we can see that each displays very different viscosity characteristics as a function of temperature. This is due to differences in formulation, pigments, fillers, binders, additives, etc. To obtain acceptable performance from each color, we must either make changes in the operating parameters of the application system to compensate for these viscosity variations, or we must consistently deliver the paint to the point of application at its optimal temperature. Carrying through our example, if a constant 26-second viscosity is desired, we see the black must be run at about 21 degrees C, the muslin and warm beige at 24, the charcoal at 26.5, and the putty just north of 29 degrees C. Along the way, chemists figured out that water, the universal solvent, would be a much better alternative to address the environmental concerns of solvent-borne coatings. And somehow, there came to be this prevailing myth that waterborne coatings don't change as a function of temperature, likely based on the belief that water is unaffected by changes in temperature. The reality, however, is quite different. Here we see a plot taken from an old viscometer data sheet. It shows that water goes through a viscosity change of 2 to 1 between 10 and 40 degrees C. While you don't think of a glass of iced tea being more viscous than a cup of hot tea, it is. Furthermore, when compared to common solvents like MEK, acetone, toluene, alcohols, and the like, not only is water more viscous, it has a steeper temperature versus viscosity curve. As a result, waterborne coating formulations are often more sensitive, not only to variations, but also to extremes in temperature than their solvent-borne cousins. So there goes that old claim that waterborne paints aren't affected by temperature. In reality, some of the most temperature-sensitive coatings we've ever worked with were waterborne. But the most significant change comes with a comparatively recent introduction of 100% solids UV cure coatings, which have been hailed as a means to reduce solvent use and to allow coating of substrates such as wood and plastic that cannot be oven cured. From a processing perspective, however, these are a little different from their solvent-borne and waterborne counterparts. They are comprised of an oligomer resin that is quite viscous. To bring that down to a usable viscosity, a monomer reducer is added. This shows the curves for a typical UV cure coating in its pure state and when blended with monomer reducer at 70-30 and 50-50 ratios. We can see the high viscosity of the resin and the dramatic effect of temperature on that viscosity. Looking only at the normal ambient range of 20 to 40 degrees C, the Valspar solvent-borne paint we looked at earlier displays a 2.5 to 1 change in viscosity as compared to 10 to 1 for this UV resin. As with solvent, the viscosity of the monomer reducer is orders of magnitude lower than the resin, and so has a significant impact on the viscosity of the blend. Though the reduced curves appear quite flat, this is an optical illusion caused by the large vertical scale required to display the entire 100% resin curve. On closer examination, these are all exponential curves and so are much easier to analyze when we change to a logarithmic vertical scale. To demonstrate the similarity between the characteristics of solvent-borne, waterborne, and 100% solids coatings, we will make the assumption that we are substituting this 100% solids coating for the solvent-borne coating above in the same application, and therefore desire to have the same 26-second viscosity. A viscosity conversion chart reveals that 26 seconds in a Zon 4 cup is equivalent to about 325 centipoise. If we look at 325 centipoise on this graph, some interesting coincidences appear. The first is that the 50-50 blend is at 325 centipoise at 20 degrees C, or about 68 degrees Fahrenheit. Following our assumption then, we can hold the 50-50 blend at 20 degrees C and make a direct substitution in our process. But as with solvent-borne coatings, the goal is to minimize reducer to control cost and improve performance. Following to the right, we find that at 40 degrees C, the 70-30 blend is also at 325 centipoise. At the extreme, the 100% resin is at 325 centipoise at 70 degrees C, and it could be used without reducer at that temperature, but this is too hot and requires special system design considerations to protect both the parts and the operators. Having defined the similarity and interaction between viscosity and temperature for modern coating materials, we can now turn our attention to their impact on the two most common application processes, spraying and rolling. There are as many different spray systems as there are engineers to design them, but they all boil down to the same basic configuration. In addition to the basic system layout, this thermal model shows calculated temperatures at various points throughout the system. Though the temperature may be important at various points throughout the fluid delivery path, to maintain a consistent viscosity and to control pressure drop, there is only one temperature that determines the quality of the finish, and that's the temperature of the paint leaving the nozzle. This is commonly referred to interchangeably as the point of application, point of dispense, or point of use. One of the most significant factors in spray application is consistency of atomization. The orifice size and shape is fixed in any given applicator, so the atomization produced by the orifice is a function of the flow, pressure, and viscosity of the coating presented to it. In most applications, the pressure is held constant by a regulator. Therefore, the only variable to be considered is viscosity. Higher viscosities produce larger, heavier droplets, which result in a heavier film build, and film thickness is an important factor in color match. This also impacts flow out and thus surface finish qualities such as gloss. Adequate film build is essential to good finish quality, but excessive film build can have a negative impact on the result. Too much paint on the surface not only increases paint usage, but can also result in runs, sags, and orange peel. At the extreme, this heavier film build can even result in solvent pop as the solvent trapped in the lower layers of the film migrates to the surface and escapes during the curing process. Or, in the case of 100% solids, uncured coating in the lower layers of the heavy film where the UV can't reach. Conversely, lower viscosities produce smaller and lighter droplets, which are more susceptible to being caught in the booth draft and directed away from their designated target. Even in electrostatic systems, this can result in greater overspray and lower transfer efficiencies. This results in a lighter film build, which again can have a significant impact on color match. These smaller droplets also present more surface area to the air, which promotes solvent evaporation through the droplet's surface. The rate of evaporation, which increases with temperature, can result in dry spray, with a significant portion of the solvent lost before the droplets even reach the target surface. With insufficient solvent in the coating to facilitate flow out, gloss suffers. This can also have a negative impact on adhesion. Fortunately, evaporation is less of an issue with 100% solids coatings. In short, consistent atomization is essential to consistency of deposition rate, which is the key to transfer efficiency, cure rate, color match, surface finish, and adhesion. In most spray systems, atomization is directly affected by viscosity, which is directly related to temperature, and therefore, consistent atomization requires consistent coating temperature. But atomization is not the only delivery factor affected by changes in viscosity. To create these coupons, orifice size, pressure, path, speed, and distance and angle to the part were held constant while the coating was sprayed. Only temperature was varied, which in turn changed the viscosity. The most obvious change is in the width of the fan pattern, but perhaps even more important is the impact of viscosity on spray consistency. Above 35 degrees, the coating is thin and uneven. You can see the substrate peeking through. In the 30 to 35 degrees C range, the coating is smooth from edge to edge. This is the optimal operating temperature for this process. Below 30 degrees C, we see heavy edges beginning to appear, which are often associated with striping on the finished part. As we move into the 25 degrees C range and below, we see the combination of very uneven coating surrounded by heavy edges, which makes it very difficult to get a smooth, even coating on the finished part. Without a smooth, even coating, finish quality will be compromised. An operator must compensate for these changes by making adjustments to the pressure regulator and/or through eye-hand coordination, adjusting overlap and respraying thin areas. At lower temperatures, due to the heavy edges, the overlap area can produce too heavy a film build, resulting in the run and sag, orange peel, and cure issues we've discussed previously. When robotics are employed, eye-hand coordination is not a factor, and the problem can be repeated over and over again. The surface can end up looking like this. Here we can see that the thinner film areas will cure more rapidly than the thicker film areas. This is no different between oven cure finishes and UV cure ones. The uneven surface will have a negative impact on gloss due to the different reflection angles from the surface and the various layers of the coating. To make matters worse, if the thinner film areas are within spec, the thicker film areas represent excess coating being applied, and that equals excess cost. In both instances, it's also possible to create blisters, either from solvent or air entrapment under the cured surface of the coating. In the case of UV coatings, this can also represent uncured material, especially a problem in pigmented coatings when the lower layers are shadowed and do not get enough light to cure them in the time allotted. If the viscosity can be controlled and the system set up such that atomization, deposition, and film build are even across the part, the cure will be even and the result significantly more predictable. This smoother surface will also produce a higher gloss. The goal, then, is to stabilize and optimize the viscosity of the coating material at the point of use, which in spray systems is the nozzle orifice. No other material temperature in the system matters to the stability of the coating process. Changes in viscosity can be gradual as the temperature climbs throughout the day or falls throughout the night, or it can be rapid as thermal losses create uneven temperatures throughout the dispensing system. This is especially true where coating temperatures are elevated above ambient. This shows the thermal loss from a dispense valve to ambient over time on a robotic spray system. When the system is allowed to sit idle for more than a few minutes, breaks, shift changes, part changes, downtime, etc., the loss can be significant. Here we see the effect of a dispense valve open to the air during a break and the impact that it has on coating temperature. The 11 degrees Fahrenheit lost over just 10 minutes equates to a 400 centipoise increase in viscosity for the 70-30 blend in the UV coating we were discussing earlier. Note that insulation slows thermal loss. It does not prevent it. Here we can see what happens when the cold material reaches the gun and is sprayed. While the cold material is being sprayed, the fan pattern is narrower and the film deposition is heavier. As soon as that is through the gun, the warmer coating behind it results in a wider fan pattern and a lighter film deposition. This would likely create unacceptable results, even in the hands of a skilled spray operator, but most certainly in a robotic application. An operator might purge this from the dispense path prior to spraying, and a robot could be programmed to do so as well, but this represents unnecessary coating material waste. There are also a host of different roll coating operations: pre-coated steel and aluminum strip, fabric and fiberglass web, juice box, corrugated and adhesive label stock, and can-making sheet, just to name a few. One of the fundamental differences between spray application processes and roll coating processes is that instead of being sprayed from a single point orifice, the coating is applied all along the width of the face of the applicator roll. Any variation of temperature, meaning viscosity, along this path will result in a variation in coating film build. In addition, friction between the rolls generates heat. Therefore, the mechanics of the coating system will endeavor to increase coating material temperature and thereby reduce its viscosity throughout the coating cycle. Analysis of such a system requires a different approach to measurement, as shown here, where we can see the probes of the packed data collection system in place across the nip. This is the last opportunity to measure coating temperature prior to application and allows us to identify temperature variations from edge to edge and over time, or head to tail on the coil, which results in variation in DFT. We refer to this as the thermal profile of the nip. The heating phenomenon is clearly demonstrated in this plot, which shows the temperature profile of a roll coating system without temperature control over an hour's time. Plotted here are ambient temperature, drum temperature, and the temperature at 8 points across the width of the roll. This graph reveals many interesting details about the roll coating process. The first thing that catches our eye is the increase in coating temperature from 26 to 32 C over the course of this hour. This represents head-to-tail variation. Remember back on slide 2 when Valspar told us our window of operation is just 3 degrees C? Here we have nearly doubled it. It's also important to note that ambient rises just over 3 degrees C over this same period. The difference between the ambient increase and the process increase is the result of the friction we just described. This friction-generated heat explains why controlling the ambient temperature in the booth cannot accurately control the temperature of the coating. The problem is that this friction also creates a 3 degrees C variation across the width of the rolls, which we see as the vertical displacement of the traces. It's all because of the flow dynamic in the coating in the system, but manifests itself as edge-to-edge variation. It's actually easier to see and analyze if you view it time-lapsed like this. This is an excellent example of how these swirls and eddy currents affect the performance of the coater. We call this an uncorrected profile. Of particular interest is the stark difference between pan 5 and pan 6 over just a short distance. It is nearly impossible to compensate for this stark change using just the adjustments at each end of the nip. And here we can see the effect of this uncorrected temperature profile on edge-to-edge film build. We can see that the areas of higher temperature result in lower viscosity, which produces a thinner film, whereas the cooler areas result in higher viscosity and produce a heavier film. Note how much it looks like the variations we saw in the spray system. Yes, that's funny, but in all actuality, it doesn't matter how you apply a coating. If it's not smooth and even and thoroughly cured across the entire surface, the result will be issues with the quality. And so, the goal is to stabilize the viscosity of the coating material at the point of use, which is actually the material at the junction of the nip. No other material temperature in the system matters to the stability of the coil coating process. This shows the same system after profile correction. We can see that in the corrected profile, variations are minor and dissipate very quickly. This shows that the total temperature variation across the width of the strip has been reduced to less than 1 degree C. Based on the Valspar data we looked at earlier, this translates to a total edge-to-edge viscosity variation of about 0.8 seconds, or just 20% of the total operating window. The resulting flat, even coating shows that the coating process is operating in its most efficient and economic mode. In each of these cases, it is clear that stabilizing the process requires controlling the temperature of the coating at the point of use. Though the approach for each is unique, the end result is the same. Stabilizing the coating temperature stabilizes its viscosity and helps us to bring the process under control. It is just as important to control the temperature at the optimal value. Often, with modern coatings, that optimal value is in the middle of the ambient temperature range. In many cases, and in many climates, it is necessary to heat the coating during the cool morning hours and cool it through the warmth of the afternoon. Seasonal temperature variations are generally even more extreme, accentuating these requirements. We have also demonstrated that many systems generate friction as a part of the delivery and application process. This friction manifests itself as heat, which must be removed by the temperature control system. In virtually all modern coating applications, a system capable of both heating and cooling, and of switching seamlessly between the two as required without operator intervention, is essential. Recent advances in both methodology and thermal transfer devices make temperature a tool that can be utilized to protect the integrity of virtually every coating and optimize the performance of both the coating and the application process. These move temperature control from the bulk supply at the beginning of the process to the point of application, where it can have a more positive impact on the overall performance of the coating process. This adds another important parameter to the list of those that combine to control the process. In conclusion, if the parameters of a proven coating recipe are held constant, the resulting deposition pattern will be consistent and repeatable. And aren't consistent and repeatable two terms that we want associated with our process? Though modern coatings may be very different chemically, when it comes to dispensing and applying them, the methods employed and their behaviors within those systems are very similar. This is especially advantageous where waterborne or 100% solid coating formulations can be substituted for more conventional solvent-borne versions to gain significant performance and/or environmental benefits without incurring major rework, downtime, and cost in the implementation. In each case, temperature variations result in viscosity variations that undermine those advantages. In fact, these newer, more modern coating formulations are often even more temperature sensitive than their older counterparts. Modern temperature control systems utilize innovative methods and devices to assure that temperature-based viscosity variations at the point of application are eliminated and that consistent, repeatable performance can be achieved independent of changes in ambient temperature and/or processing conditions. This converts temperature into a tool that can be used in conjunction with other tools like pressure regulation, speed control, and the like to assure that the outcomes of the coating process are predictable and repeatable and advance the goals and objectives of your business. I'd like to thank you for taking the time to join me for this presentation. Though we've only scratched the surface of the subject of temperature control in painting processes and the impact that it has on quality and performance, I hope that this cursory introduction has given you a different window through which to view your operation. I encourage you to contact us to gain a more in-depth perspective of how you can reduce costs, improve quality, and shorten your production cycle by controlling the temperature variable in your painting system.